Hi, I'm Noah Van Beurden. I'm from Percy, Pennsylvania, and I attend Penrith High School.
Hi, my name is Owen McElhaugh. I'm from Richboro, Pennsylvania, and attend Council Rock High School South.
Hello, my name is Seth, Akins, and I am from Faircrest, Washington, and I go to Curtis Senior High School.
I'm Jaral Arroyo-Jefferson from Miami, Florida, and I attend Ransom Everglades.
Hi, my name is Alisha Chen, and I am from San Jose, California, and I go to Basis Independent Silicon Valley.
Hello, my name is Omolola Falana, and I am from Plainfield, New Jersey. I attend Union County Magnet High School.
My name is Marion Fusco. I'm from Brooklyn, New York, and I attend Millennium High School.
Hi, my name is Hope Dickson, and I'm from Falls Church, Virginia, and I go to Georgetown Visitation Preparatory School.
Now, let's move on to the inspiration behind our project, which comes from the UT Austin Drone Estimation Lab, or DEL. The DEL project is working to create an accurate location estimation for drones by running real-time sensor inputs through an extended Kalman filter, or EKF. This process involves fusing outputs from different sensors on drones. By doing so, they are able to create 3D error ellipsoid visualizations. One significant achievement of the DEL project is their error ellipsoid accuracy of 97.1%. However, it's worth noting that while DEL has performed location estimation, they have not yet implemented an extended Kalman filter. This gives us the opportunity to build on their work and integrate a Kalman filter into our project to achieve even greater accuracy in drone position estimation.
To build on the DEL project, we felt the best way to improve accuracy was to incorporate more data through the added sensors such as LiDAR or a camera. Then using an extended Kalman filter, we would be able to fuse onboard drone IMU and GPS data with LiDAR data or camera data for more accurate pose estimations.
The main problem that our group is trying to face is that the growth of the drone industry increases air traffic, raising the risk of drone collisions with other UAVs and non-cooperative targets such as birds and kites.
Imperfect data is considered noisy. Take this sonar data collection of altitude, for example. The human eye could reason that based on the graph as a whole, the altitude would never drop by multiple meters in a fraction of a second. However, hardware inaccuracies and sensor fluctuations produce noisy data that needs to be filtered and cleaned. Our study sought to estimate position accurately by filtering noisy data from IMU, GPS, and LiDAR data with a special filter designed for aerospace applications called the Kalman filter.
Now let's walk through the data analysis process for our project. The process can be broken down into 6 main steps. During drone flight, data is recorded by the Pixhawk 6X flight controller as the drone flies. This includes all of the sensor inputs, flight data, and IMU recordings needed for our analysis. After the flight, the recorded data is extracted. We use QGround control to download the .ulog files from the drone. These files contain the raw flight data in binary format. The next step is to convert these .ulog files into a much more usable format. Using the pyulog Python package, we convert the .ulog files into .csv files, which contain the data in text format, making data analysis much easier. Once we have the .csv files, we are then able to import our data into MATLAB and choose the specific data types that we wish to Kalman filter and analyze. Then, we apply the Kalman filter to the data in MATLAB. Here, we minimize the noise and errors present in the raw data. This allows us to create an estimate of the true position of the drone. Finally, we compare the filtered results to the GPS data and videos that we took of the flight, as well as graph our filtered data to visualize the path of the drone. This allows us to evaluate the accuracy of our position estimation and make any necessary adjustments to improve it.
Let's look at the key components of the Holybro X500 V2 development kit for our drone project. The Pixhawk 6X flight controller manages the flight dynamics with advanced IMU and multiple I/O ports. The PM02D provides power and monitors battery voltage. The M10 GPS module provides precise positioning data. We use the SIK telemetry radio V3 for long-range communication. The X500 V2 frame kit is durable and lightweight, and additionally it's modular for easy assembly. 4 Holybro 216 KV920 brushless motors provided thrust, controlled by BL Heli S28 ESCs for smooth operation. 6 1045 propellers ensure efficiency in thrust and stability, ensuring our drone's reliability and efficiency in performance. Now the communication system. The transmitter or remote control sends input signals when you move the various switches to the bound receiver on the drone. The receiver then replays these inputs to the flight controller. The flight controller acts as a mini computer, processing the inputs from the receiver and sending output values to the motor, ensuring they reflect the controls performed on the transmitter. Additionally, the flight controller continuously monitors the various sensors' values as the drone is flown.
During our building process, we organized the team into 3 groups based on their skills and interests. Each group was assigned different remote controllers and utilized distinct GPS receivers and transmitters. 2 of these groups used telemetry communication hardware included in the Holy Bro kit, paired with Radio Link and Radio Master controllers respectively. The 3rd group opted for a different telemetry network, HereLink, which required the addition of an air unit and cooling fan to their drone. All these groups successfully assembled the frames, installed the motors, and set up the Pixhogs. Additionally, each group managed to establish a stable connection between the remote controller and drone.
During the assembly of our drone, we encountered several obstacles primarily related to product issues and financial constraints. Initially, assembling the Holy Bro kit posed a challenge as the baseboard screw holes were too small for the screws provided. To address this, we used a Dremel to make holes big enough for the screws to fit properly. After we finished assembling the drone, both teams 2 and 3 faced difficulties advancing in the project because they were waiting for specific 2S and 3S batteries required for operation. Team 1 managed to successfully fly their drone initially, but encountered a setback on the 2nd day of testing when the motors caught fire, causing irreparable damage within our project's time constraints. On day 6, Team 3 faced issues with their drone's center of mass, which was unbalanced and affected flight stability. They resolved this by removing the drone's legs to regain balance and enable proper flight. Despite these challenges, we successfully got 1 drone flying by the end of the project.
We chose to test the HereLink system due to the draw of a fully pre-integrated system. The HereLink kit includes antennas, a controller, a GPS, and its own telemetry unit, the air unit. It had the potential to be the best of the 3 due to the fact that it had the complete integration and wouldn't require us to do any sort of connecting on our end. The air unit was the main center of the HereLink system and functioned to communicate between the actual drone itself and the ground control. It ultimately failed due to an unfixable battery issue. We ran into 2 main issues while trying to get the HereLink to work. The first main issue was the idea of having to get a power supply to it. The HereLink required a voltage input of around 11 volts, and with our current 4S batteries, we exceeded that voltage maximum. What we ended up doing was switching the whole system over to a 3S battery, and just connecting both the air unit and its cooling fan directly into the power supply board. The second main issue was actually communicating between the air unit hardware and the Pixhock hardware. What we ended up doing was creating specific wires that would allow us to switch between the 2 ports and actually get data flow.
The TX16S Radio Master is a versatile 16-channel transmitter widely used for controlling drones. As a transmitter, it serves as a remote control device, sending signals to the drone to execute various commands. Equipped with a large color touchscreen, OpenTX firmware for customization, and comprehensive telemetry capabilities, it offers reliability and flexibility for both hobbyists and professionals. In Mode 2 configuration, the 4 main channels control the drone's movement. Throttle on channel 3 for altitude, yaw for rotation on channel 4, pitch on channel 2 for forward and backwards tilt, and roll on channel 1 for side-to-side tilt. These controls enable precise maneuver and stable flight. In setting up the Radio Master transmitter, we encountered an issue with the transmitter configuration. We found that the throttle channel midpoint was set at 0, but a neutral position of 50 would be better suited. Adjusting the channel settings to shift the midpoint to 50 caused a high throttle warning in the Q ground control, preventing the drone from arming. Despite multiple calibration attempts, the issue persisted. Keeping the original throttle position reduced the range of motion, causing more drastic propeller speed increases with slight stick maneuvers and making the drone harder to control.
This radio link controller is an 8-channel T8S radio transmitter that features dual joysticks, switch dials, and different control modes. The radio link also comes with a RAEF receiver, which we attached to the drone so that the controller can communicate commands to it. We used this controller as a cheaper alternative to the Radio Master controller. The radio link was also quick to set up and didn't require extra batteries. The controller is more of an entry-level controller to a Radio Master.
For our software, we leveraged an open source software application called Q Ground Control. Without directly having to code our own environment for data logging or motor configuration, Q Ground Control provided easy configuration for motors and radios and MAVLink communications with the drone for live data visualization.
GPS has some inaccuracies caused by timing issues. Firstly, Because the speed of light is so fast, at about 300,000 meters per second, if the sensor reads the signal even a microsecond too late, it will record a distance with an error of about 300 meters. To minimize this error, sensors and satellites must have atomic clocks, such as this one, that are capable of recording nanoseconds. Secondly, because of how fast the satellites are moving, and the relativity of time, it is very easy for the clocks in the sensors and the satellites to become unsynced. And lastly, the problem that pertains to our project the most, GPS only works with sensors that are on the surface of the Earth. This renders them totally useless in cases of location estimation inside buildings or even on other planets.
Continuing from where we left off, let's dive into the Inertial Measurement Unit, or IMU, on the drone's Pixhawk flight controller. The IMU records the drone's acceleration and rotation rate relative to itself. It consists of two primary sensors, an accelerometer and a gyroscope. The accelerometer measures the drone's linear acceleration, detecting changes in speed in all directions. The gyroscope measures the drone's rotation around multiple axes, including pitch, roll, and yaw. Using these sensors, the IMU detects changes in the drone's position, orientation, and velocity, crucial for maintaining stable flight and executing precise maneuvers. In summary, the IMU provides essential data that allows the flight controller to keep the drone balanced and on its intended flight path.
Light detection ranging, or LiDAR, is the process of sending out pulses of light and recording the time it takes for it to reflect off a surface and come back to a sensor. With that, you're able to calculate the distance from the sensor to certain objects. For our process, we use the SlamTech A1M8, which allows us to record in a complete 360-degree 2D slice, as the actual sensor itself is able to spin. This has applications in many parts of the drone process, including both altitude measurement or object avoidance.
To demonstrate the mild inaccuracies that can occur when observing LiDAR data, and how the Kalman filter can fix them, we needed the LiDAR to observe an object from a known distance. We set a trash can 5.5 meters away from the sensor, and meticulously marked every meter between the two. Without a drone that could support our LiDAR sensor, we had to get creative. We used a cardboard box to mount the sensor to a rolling chair, and secured another piece of cardboard that reached from the side of the chair to the floor, so that we could show the sensor's exact location with markings on the ground. On the chair, we set the computer that had RoboStudio running, and using LiDAR data to record position and distance, and we set a stopwatch running to observe time of each position.
There are many ways to filter noisy data, and the primary idea behind filtering is averaging out inaccuracies within the data to predict and estimate a drone's position. Different methods include simple averaging, which is where you add all of the terms and divide by the number of terms, and this is known as a batch expression. Another way to filter is to take a moving average. When a simple average is too much to compute in a real-time onboard processor, recursive moving averages allows you to calculate real-time without storing all previous data points, because you simply update the average with each new data point instead of re-evaluating the data every time you get a new point. This way is efficient and faster. Another way of filtering is called a low-pass filter. This allows low frequency and filters out high-frequency data points, where high-frequency data point represents the noise, but each term is weighted the same. The ideal method to filter data is known as a Kalman filter. A Kalman filter is a weighted low-pass filter where past data gets weighted exponentially smaller as new, more relevant data comes in. An important aspect of the Kalman filter is the ability to tune it to specific data sets to meet analysis needs. Here you can see the original raw LiDAR data that looks spiky even though it was tracking a linear one-dimensional data set. Applying and tuning the Kalman filter allows us to create a range of estimates by changing the noise covariance variable Q. A smaller Q value, as shown on the left graph, makes a smoother line, which makes analysis easier if you were to integrate or take a derivative of your data. However, a larger Q value, as shown on the right graph, aligns more closely with the original, noisier data, thus creating a spikier graph that more closely resembles the original data points. Here you can see a comparison of position estimation between local positioning and global positioning systems from the same flight of a drone. Notice how the Kalman filter fills in gaps and holes in the dataset. Also notice how the Kalman values appear shifted to the right of the original dataset values. This is because using the Kalman filter uses previous data in addition to current data to make its predictions and estimates.
Even though we had difficulties in the drone build process, we did have significant results. We found that the Radio Master controller and standard telemetry radio provided the most stable communications. By running the collected data through the Kalman filter, we achieved a noise reduction of 41% in the IMU measurements. For the LiDAR measurements, the Kalman filter was particularly effective in removing extreme outliers from the dataset, helping to create a more realistic representation of the operating environment for obstacle avoidance, especially crucial in autonomous flight systems. The Kalman filter halved the average error in the LiDAR measurements. This study demonstrates that IMU and LiDAR data refined with the Kalman filter can accurately estimate drone position. These methods show potential for position estimations in areas where the GPS reliability is a big concern.
We realized throughout the building process we had spread ourselves too thin and ran into many hardware roadblocks, leaving barely enough time to add another sensor or a coprocessor or even get to any of the data processing. So instead of fusing data together, we targeted to filter noise out of the GPS and IMU data we already had. Rather than just focusing on tuning out noise, our next steps would be to incorporate more sources of data, meaning adding another sensor, whether that be a LiDAR or a camera, and to fuse that data with our current GPS and IMU data to better find a more accurate position.
Working on the FUNPEDS and ZQ projects has given me practical aerospace experience and solidified my passion for space exploration. Interacting with NASA professionals during the SEAS internship provided critical career insights and confirmed my goal to become a NASA engineer.
As a NASA SEAS intern, I was able to meet so many professionals in the field, such as NASA astronauts and researchers. Their passion for their work is so strong, whether that be Earth exploration, moon exploration, or some other planet, or just leading a team. I was truly inspired and really opened up my eyes to the different avenues in the job market. I also had the opportunity to work with an incredible team focused on drone positioning. Throughout the 2-week journey, which felt so long yet so short, I learned to look for the solutions when everything felt like it was going wrong. Thank you, SEAS, for this amazing opportunity.
For me, SEAS has been a truly life-changing experience. Not only has it reaffirmed what I want to do with my life, but having such an amazing opportunity has left me incredibly thankful. I'm so happy to have had the opportunity to work in such a caring, inspiring environment that, although challenging at times, pushed me to be the best version of myself.
My time spent in the NASA SEAS internship was a phenomenal experience that I would like to do again. The internship has piqued my interest in aerospace engineering and space exploration. It has also connected me with extraordinary people who share my passions for space exploration and engineering. This was a great experience, and I really enjoyed the work we conducted during this research project. Thank you so much for this opportunity.
Being a NASA SEAS intern has been a once-in-a-lifetime experience. I've had the amazing opportunity to meet and hear from people directly involved in aerospace through the speaker series, which has been truly eye-opening. I'm so grateful as well for the opportunity to meet and connect with so many like-minded peers during my time in Austin. Working on this project with my team has confirmed my interest in aerospace engineering.
My time with the NASA SEAS program really boosted my interest in aerospace engineering. Working on our team project taught me so many strategies and softwares that can be applied in the field. It was hands-on and eye-opening, making me even more excited to keep exploring aerospace engineering.
As a NASA intern, I have really enjoyed contributing to a real ongoing research project where our study will aid the future of commercial drone use. I've especially enjoyed learning about the graduate-level math behind the Kalman filter because I was able to visualize and produce real-world applications of this math. My NASA SEAS internship has been an amazing opportunity, not only to learn from and contribute to the scientific community, but also to network and work with other like-minded peers and mentors fascinated by space and aerospace engineering.
Before this experience, I had no idea what career path I wanted to pursue. But my experience as a NASA SEAS intern has taught me so much about the specifics of and science behind much of the work that NASA does. But even more so, it's taught me how to work with other people, to troubleshoot and work around issues, and to never give up, even if it feels like all the cards are stacked against you. I am extremely grateful that this experience has opened my eyes to so many interesting job options, and specifically has inspired me to consider a career as an astronaut.
At this point, we'd like to thank our mentor, Mr. Nokes, for the guidance you offered us on this project throughout the time we were in Austin. We'd also like to thank Mrs. Baggio and Mrs. Miller for helping to manage SEAS. We truly appreciate all that you have done to make our time here such a great experience. We'd also like to thank Mr. Barker and all of the other helpers and mentors who helped SEAS run smoothly. And finally, we'd like to thank all of our fellow interns who we loved getting to meet.